Hello everyone, welcome back. My name is Wasim, and in this video tutorial we'll see how to plot grain size distribution curve and calculate the value of D10, D30 and D60. We'll also see how to calculate uniformity coefficient Cu and the coefficient of gradation Cc. So this is the problem statement given along with this data in the table. So what is given to us is a sieve number, diameter in mm, and weight retained on each sieve. Okay, so usually the value of sieve number and diameter, these are different if you are referring to US standard or any other standard, but if you are referring to Indian standard, these values are both similar. So anyway, it is irrelevant. I just wanted to point it out. So the important thing before we start doing the calculation is to notice that the column number 3 which is given to us is in the form of soil retained on each sieve, not the passing. Okay, passing through each sieve is a different data. Retaining on top of the sieve is a different data. So if passing through each sieve is given, numerical becomes much more easier. For retaining value, we have to do some extra steps. So what are these steps? Let's see. So the first thing is the calculation of percentage retain on each sieve. If you look at the column number 3, you will see the values are given in the grams, not in the percentage as compared with the total amount of soil. So the first thing that we'll do is calculate a new table in which we'll have another column where we will have percentage retain. So in order to do that, the first thing that we should do is calculate the total weight of the soil. How we can calculate that? Just add all of these values. So this is what you see over here. All these values are added and that value is 617. I have written down that value at the bottom over here. That is 617 gram. So that is all the soil that is used for sieve analysis. Next thing, we'll add another column, percentage retain. So what does this column represent? This column represent if let's say 617 is the 100% of soil, then how much is this 20%? 20 gram. So how we can do that? Just simply if we can do the cross multiplication. For example, for sieve number 4, that is the first sieve, what we'll assume 617 is 100%. So 28 gram equals to x, that is for sieve number 4. So when you do the cross multiplication, the first value, that x, it comes as a 4.35. Similarly for sieve number 10, we can again do the cross multiplication. 42 into 100 divided by 617, that is 6.81%. So this is how we calculate percentage retain on each sieve. So just repeat the calculation for all of these values and you will get this column something like this. So just verify all these values. I have verified them once and twice and everything seems accurate. But if there are any mistakes, please let me know. Okay. So next, step number 2, calculation of cumulative retain. Now this is percentage retain but in the form of cumulative. The word cumulative means successive addition, or you can just say it is a combination of different values. So the formula is very simple, percentage retain on the top sieves. Let's say for example, first value that we'll look at sieve number 10. Why I'm not doing 4, I'll do the 4 later on, but I just wanted to explain you the concept. Once you understand the concept, you can do all the calculation. So let's focus on sieve number 10 first. So as per the formula, that value will come as 11.34. Now how does that value come? That value comes as a addition of successive values of sieve number 10. So that value is on sieve number 10, it is 6.81 plus you add the value above it. So how much is that value? 4.35. So you get 4.35 plus 6.81. You will get the value 11.34. This is how we do the cumulative percentage. Now let's look at another example of sieve number 20. So sieve number 20, that value will come as a 19.31. So how does it come? It comes as a successive addition of all the values above sieve number 20, including sieve number 20. So this is 7.87 plus 6.81 plus 4.35, and that value will come as a 19.31. This is how we calculate the cumulative percentage. There is another easier way, which by the way you should use. So what is that way? You just add these two values. What are these two values that I'm adding over here? Just pay attention. So what I'm doing is, instead of taking a combination of all the values above it, I'm just adding these two values. Let me just these two values. When I add these two values, I'll automatically get 19.31. So this is how we do it. So next, for this value, how I can do that? Just add these two values, 20.75 plus 19.31. You will get some value, that is 39.81. Okay, still I have not explained you how this value at sieve number 4 will come. So as it is a cumulative, it means this 4.35 plus the value above that sieve. So 4 number sieve is our first sieve, so the value above it will be 0. So 0 plus 4.35, you will get 4.35. That's why this value, percentage retain and cumulative percentage retain, are the same. Okay, so next what we can do is, once we got this value, so what you can do is just add these two values, then you will get this 75.70. Then add these two values, then you will get 89.63. Add these two values again, and you will get 96.11. Add these two values, you will get 100%. So this is how we do the calculation of cumulative percentage retain. Next thing is calculation of percentage passing. This is probably the last column that we have to calculate. And this is very easy. Let's say this is a one particular sieve, and on top of this sieve, 10% of soil is being retained. So 10% is retaining or staying on top of this sieve. So if 10% is retaining, how much is passing? Passing will be 90%, that is 100% minus 10%. So percentage passing is nothing but whatever is 100% minus whatever is retaining on that sieve. So this is very simple. So look at the formula. Percentage passing through a sieve is 100% minus cumulative percentage on that sieve. So for example, let's look at sieve number 4. On sieve number 4, percentage passing through sieve number 4 will be 100 minus this value, 4.53. So 100 minus this value will give you this value. Next, if you look at sieve number 10, so 100 minus 11.53 will give you 88.65. Then again next, 19.13, 100 minus 19.13 will give you 80.87. 100 minus 39.88 will give you this value. 100 minus this value will give you 24.30. So this is how we will calculate our last column in the table. So this is a very easier method, but all you have to do, just remember how to calculate the particular value. Okay, that's very easy. Nothing in this numerical. Okay, so now let's move to our step number 4, that is calculation or the curve plotting. So when we plot the particle size distribution, what values we are plotting? We are plotting diameter on x-axis and percentage passing on y-axis. So these two are the values that will come onto your graph. A very important thing that you must notice over here is that the value of pan are not plotted on the graph. Why they are not plotted? Because pan does not have any diameter. Because pan is a container which does not have any holes, so nothing is passing through it. So that's why we don't plot it. Okay, so let's get back to curve plotting. Now these two values I have separated from the table. So I have diameter on x-axis and percentage on y-axis. Let me just have some water very quickly. Okay, fine. Next, chalo. So this is what a semi-log paper looks like. And remember, these you cannot plot effective size or particle size distribution curve on your normal graph. You must use a semi-log paper. There are three different types of papers. Graph paper, one is that you use regularly, and other one is semi-log, and the third one is log paper. So what is the difference between your semi-log normal graph is this. If you look at the x y direction, vertical direction, you will see that the values or these lines are separated at equal distance. Okay, in y direction all the boxes are of same size, but in x direction, if you look at in this direction, the boxes are of variable size. This kind of variation is called as a log variation. So why do we use it? I'll explain you later on why only semi-log paper is required, why you cannot use a normal paper. I'll explain you that little bit later. Just let me remove this one. Yeah, okay. So this y direction or the direction of equal distance boxes is called as arithmetic scale, and this x direction where there is a log variation is called as a log scale. Now the next step is to plot the scale. Scale plotting is probably the most important uh, aspect of understanding the semi-log plotting. So first, the easier one on y-axis, scale on y-axis. Scale on y-axis, what I am taking is 1 unit as a 4% of the soil passing. Now, what does it mean? It means that, let's say, if I start in y direction with 0 and I reach to my first line, that will be 4%. If I go to the second line, it will be 8%. Next will be 12, 16, and 20. So this is equal distance variation. As usual that you do in case of your normal graph paper, you can also use 10%, 20%, whatever you want. So if I decide that 1 unit equals to 4%, what values do I get on x-axis? I guess first value 0, second value over here, that is the first line, 20, then next I'll get 40, 60, 80, and 100. So this is what you see over here: 0, 20, 40, 60, 80, and 100. You can also use 0, 10, 20, 30, 40, and in that case your 100 will be on the top over here. But I don't want to use the entire graph paper because sometime I plot multiple graphs on a single semi-log paper, so you can save the space, or you can. And other thing is that if you use a very big or very small variation, 0, 10, 20, your graph will be like very big like this. So I don't want that. I want a very small graph which I can fit in a very small paper, something like this. So that is why I'm using this kind of scale on x-axis. So this is easier. That is what we usually do. But when you go for x-axis, things become little bit complicated. So one thing that you should notice, my origin on x-axis, I'm not starting with 0. Okay, I'm starting with some value 0.001. Okay, first of all, why it is not 0? The reason, the log of 0 is always a positive value. It is never 0 or less than 0. So you cannot have, mathematically, you cannot have 0 on x-axis because it is a log scale. So 0 is not there. Okay, now why I am taking this first origin value as 0.001? Why I am not taking 1, or why I am not taking 0.01? Why this value? Because in order to do that, why I have taken that value is, first look at the smallest diameter in your table, that is 0.00, sorry, 0.075. Now, let's say for sake of argument, if I take a value 0.1, first value as a 0.1, in that case, I will not be able to plot this value. Okay. If I take the value 1, I will not be able to plot all of these values. So that's why I have taken a value 0.001 so that I can plot 0.75 somewhere over here. Okay, so when you decide the origin on the x-axis, it should be always less than the smallest value that you have over here. Okay, so that's why I've taken 0.01. Let me remove all of this. Now next, so how do we take other values? So just like in case this was 0, then 20. Now what will be the value over here? So in log scale, the value increase rapidly. So what actually happens is, so this first value that you have over here, this value becomes 0.002. Okay, so this value will be 0.002. The next value will be 0.003. Next value will be 0.004, 5, 6, 7, 8, 9, and then 0.01. Something like, let me remove this one, something like this, 0.01. Then after that, our cycle, though this is called as the first cycle, second cycle will be 0.001, 0.0, 0.01, 0.02, 0.03, 4, 5, 6, 7, 8, 9, and then 0.1. Similarly, then 0.1, 2, 3, 4, 5, 6, 7, 8, 9, then you will get the value 1. Then after that you will get 10, after that you will get 100, then 1000, then you will get 10,000, then you will get 100,000 or 1 lakh. So that is how the log scale variation is there. So that is why what I have written, if you look at x-axis, my scale is 1 unit equals to 4%, but on x-axis my scale is not constant. So I have written on x-axis we are having a log scale. Now let's come back to our my earlier statement. Why do we use semi-log paper? Semi-log paper is used because of to compress the data. Let's say in a particular data you have two values. Let's say one value you have is 1 mm and other value that you have is 0.001 mm. Okay, so if you want to plot these two, let's say these two are the values on x-axis. So if you want to plot 1 and 0.001 on same your normal graph paper, you cannot do that, because let's say you start with 0, so 0, then 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and then by the time you reach to the 0.001 or 1, you need at least 1,000 of these lines, so which is not possible on a normal graph paper. You need a very long graph paper. So in order to compress that data, we use semi-log paper. Okay, because 1 and 0.001 there is a difference of 1,000, and you cannot plot a difference of 1,000 on a normal graph paper, but over here you can plot any kind of data using a semi-log paper. So basically semi-log paper is used to compress the data. Anyways, enough of this. Let's go back to the plotting. So what I'll do is I'll plot my first point over here. So this is, once you do that, the plotting becomes like as you do usually on a normal graph paper. You plot x and y point. So first my x point is for first set of value. These are my x and y coordinate. So x is 4.75. So this is my 1 over here, 2, then 3, then 4. From the 4, I'll go just little bit ahead of 4 and I'll point 4 over here, and then from that 4 I'll reach to how much value? 95%. So this is how I'll plot this first point. Then I'll plot the second point, 2 comma 88.65. So this is, just let me remove all of this. So this is my 1 and this will be my 2 over here. Let me just zoom in and show you where will be the 2. So this will be my 2, the red line that you see, second red line after 1, that will be my 2, and 88 will be somewhere over here. So this is my 80. So this is 84 and this is 88. So I'll get second point somewhere over here. So similarly, you keep on plotting all these XY coordinates and you get a point series like this. Then you join these point series, which looks something like this. Sorry, I could not find semi-log paper nearby my area, so I could not plot them. I asked my student to send me the graph that they have plotted in our class, but none of them sent me. So I could not show you the real work, but I have this value over here. So this is what the curve actually looks like. Okay, so you plot all these points. This is your first point, 4 comma 95 something. This one is 7, second point 2 comma 88 point something. So you keep on plotting this point, then you join them using a smooth curve. So if you use the French curve, you will get a very fine looking curve. Now, what about the calculation? Now we have to do this calculation. In step number 4, we first determine these values D10, D30 and D60. By the way, this D10 is also called as the effective size. This name is given by Alan Hazen. We'll not go into the detail, but we'll determine these values using this graph. So on x-axis we have percentage final, sorry, on x-axis we have particle diameter, y-axis we have percentage final. Now how do we determine D10, D30 and D60? So the first thing that we should do is we should mark where is 10%, where is 30% and where is 60%. So corresponding to this 10, 30 and 60, I'll mark 10, 30 and 60 on my y-axis. Then from this 10% line, 10% point, I'll join a horizontal line by using scale, not like this, what I'm doing. From this point, I will drop this line on my x-axis. Okay, so wherever this vertical line meets your x-axis, and remember what is on x-axis? The diameter in mm. So wherever this line cuts your x-axis, that becomes your D10. Okay, so if you look at this, this is, I'll show you a little bit zoom. So this is my 1 over here, sorry. So this is my point 1 over here, I think, if I'm not wrong. So this is my point 1 over here, and this will be my point 2 over here. So my D10 is somewhere between point 1 and point 2. So it is less than 0.2. So let's check. So this is the value of D10. So 0.14. So this is how we determine the value of D10. Similarly, we determine the value of D30 from 30%. Join this line, drop it on x-axis like this. Just let me remove everything. I'll show you once again. From 30, yeah, sorry. From 30%, draw a line wherever it meets your curve. From that point, drop a vertical line, something like this. So this is my point 1. This is my point 2 over here. So this will be, I think, 0.3. So my D30 is less than 0.3. So that will be 0.27. Similarly, you can determine the value of D60 using this value. So if you look at this, this value is slightly greater than, I think this is slightly greater than 0.3. So that value is 0.42. Okay, so it's very easy once you do it with your own. Use the same data, plot the curve, determine all these values, And if there are any problems, let me know into the comment box. Okay, next, step number 5. Just let me have some water. Yeah. So step number 5, calculation of uniformity coefficient, Cu. So this is the formula for Cu, d60 by d10. We already calculated d60 and d10. Just put them into the formula. That is 0.42 by 0.14. This is point d6, d10. This is your d60. Just put them into formula. You will get the value of Cu as 3. Similarly, calculation of coefficient of gradation Cc. This is the formula d30 square by d60 into d10. Just put the values that we have calculated like this, and you will get the value of Cc as 1.2. So these values Cu and Cc, they are used to classify the soil. So already the numerical is being quite long, so I will not explain you how to classify the soil using the value of Cu and Cc. Maybe in future I'll make a video on it. That's it in this numerical. Thank you guys for watching. And if you want a solution for this numerical, I have given the link in the description. You can go and download that numerical from there. Anyways, you guys take care.